Next, I'm going to discuss an important theorem. It can be stated like this. Angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Now, if you visualize, it's a very simple theorem to understand. If I take a circle like this, if I consider an arc PQ here, angle subtended at the center and to the angle subtended at any point on the remaining part of the circle, ratio between this angle to this angle is 2/1. I'll refer to this theorem as 2/1 theorem. It is not called 2/1 theorem, but I'll be using 2/1 theorem for reference. Now, this theorem can be easily proved and it's widely used while solving questions. So let's understand the proof for this theorem in the conventional way first, and then we will understand that later in much more easier and interesting formats using diagrams. So for that, let's get into the proof. What is given here? In a given circle, arc PQ is subtending an angle at the center. That angle is angle POQ. And at any point, let's say A on the circle, the angle subtended is angle PAQ. So we need to prove that angle POQ equal to 2 times the angle PAQ. To prove this, first join AO and extend it to B. Now in triangle OAQ, angle OAQ equal to angle OQA, because they are the angles opposite equal sides. Why equal sides? Because OA and OQ are the radii. And we can write angle BOQ equal to angle OAQ plus angle OQA, sum of these two angles, because exterior angle equal to sum of interior opposite angles, which in turn can be written as 2 times angle OAQ, because these two angles are equal. Now that's the first statement. Similarly, in triangle OAP, we can write down angle OAP equal to angle OPA, because they are angles opposite equal sides. OA and OP are the radii. And angle BOP equal to this angle, that is angle OAP plus angle OPA, sum of remote interior angles, which in turn can be written as 2 times angle OAP. Now take that as the second statement. Now if I take sum of first statement and second statement, what I'll get is angle BOQ plus angle BOP equal to 2 times angle OAP plus angle OAQ. Now this in turn can be written as sum of these two angles, that is BOP and BOQ is nothing but angle POQ. That's equal to 2 times angle PAQ, because what is PAQ? PAQ is nothing but sum of angle OAP and angle OAQ. So thus, hence the theorem is proved. That is angle POQ, which is angle subtended at the center, is 2 times angle PAQ, which is the angle subtended at any point on the remaining part of the circle. So it's a very simple theorem. This way we can understand the 2/1 ratio between the central angle, that is angle POQ, to the angle subtended at the one of the remaining, it can be any point on the remaining part of the circle, and that ratio is 2/1. It's an important ratio. I'll call it 2/1 theorem when it comes to circles and arcs. So just to summarize, even though there are 3-4 steps, but effectively it's nothing but in this circle, first the central angle, we'll take these two angles are equal, and sum of these two equal to this this particular angle, which is angle BOQ, and these two angles are equal. Sum of these two equal to this particular angle, which is BOP. Now sum of these two obviously will be 2 times sum of these two. Thus it can be easily proved. Just that while writing in the exam, you'll have to write step by step by naming the angles. But when you visualize, it can be understood in exactly 30 seconds. Like first you take these two equal, sum of these two is this one. Then you take these two equal, sum of these two is this one. So because of that, so you are getting this angle as 2 times this has 2 times this. So sum of these two will be 2 times sum of these two. Very simple. Now let me simplify this 2/1 theorem with just one intuitive movement. So if I take a circle like this, we know that POQ by PAQ is 2 by 1. Now why it's 2 by 1? To understand, I just need to, PA is a line, I just move PA so that it becoming PA dash where it's a diameter. Now in this case, if this angle is 1, this is also 1 because they are opposite equal sides. So this 1 plus 1 will directly become 2 in a single step. So in the proof which we did previously, the conventional proof, we are doing this in 2 steps, but this is an interesting way to relate to 2 by 1. Very simple, right? If this is POQ, this was PAQ, just move this line so that PA dash is the diameter. Now 1 adding up to 2 because that's the external angle, exterior angle, and some of interior opposite angles. This is a very simple method to relate to 2 by 1. And here we can move PA to PA dash because A and A dash are nothing but they are just 2 points on the remaining part of the circle. So whether I take A or A dash, the theorem is still applicable. That's why we can have this movement and relate to 2 by 1 in a very simple manner. We'll end up getting a lot more interesting properties. So if I take the same circle where PQ is the arc, we know that this angle by this angle is 2 by 1, same 2 by 1. From this 2 by 1, let's see how we can get more properties. So push P and Q away from each other and stop at the point where PQ is the diameter. So this 2 will become 180. In that case, this 1 will become 90. And what is this angle? This is the angle in a semicircle. That is why angle in a semicircle is 90 degree. Very easy to understand, right? We are just pushing the 2 points away from each other. P and Q. Initially, it's just a chord. PQ is a chord, or PQ can be taken as an arc also. Once you push P and Q away from each other, stop at the point where PQ is the diameter, so that this angle, since it's a straight line, it will become 180. Now, following the ratio of 2 by 1, this will become 90. So what we just did is, we just proved that angle in a semicircle is 90 degrees through visualization. Very interesting. Now, the theorem, that is angle in a semicircle is 90, can be proved. So what we did now is, I just extended, or I just showed you a special case of 2 by 1 by taking a straight angle by a right angle, because this was a straight angle and this is a right angle. That's how we proved that angle in a semicircle is 90 degree. Now, if I make you think further, if we stretch our imagination a little further, let's try looking at some more 2 by 1 ratios. 2 by 1 ratio can be written as circle by triangle also. What is the angle in a circle? That's 360. What is the sum of angles in a triangle? That's 180. There also, since you can see a 2 by 1 ratio, let's see whether we can connect this 2 by 1 theorem to a circle by triangle ratio. Angles in a circle is 360. Sum of angles in a triangle is 180. See how I'm going to connect these 2 by 1 to circle by triangle. I'm sure you're going to like it. I'll take a circle and take 3 points A, B and C. Now you can easily see that arc AB plus arc BC plus arc CA will complete the circle. Now angle subtended at the center, that is, if I join all the 3 points with the center, what we'll get is this angle to this angle we'll get a 2 by 1 ratio. This angle to this angle also we'll get a 2 by 1 ratio. This central angle to this particular angle also we'll get a 2 by 1 ratio. So these are the 2 by 1 ratios which we have been dealing with. Now, if I take all the 3 central angles together, that will complete a circle. And if I take 3 angles subtended on the circle, that is angle A plus angle B plus angle C, that will complete a triangle. So since everywhere it's a 2 by 1 ratio, that is this to this is 2 by 1, this to this is 2 by 1, this to this is 2 by 1. Let me name these angles as angle 2, angle 6 and angle 10. Angle 2 plus angle 6 plus angle 10 anyway is 360 because that's completing a circle. And angle 3 plus angle 5 plus angle 1. That's equal to 180 degree because they are the sum of angles in a triangle. So here, everywhere the ratio is 2 by 1. That is why we can, that 2 by 1 is directly related to 360 by 180. Thereby, we just connected 2 by 1 theorem to circle to triangle in a very interesting fashion. So, it's now, I'm sure, all of you understood that circle by triangle can be taken as an extension of 2 by 1. Now, what is the 2 by 1 I'm talking about? Central angle to an angle subtended at one of the points on the circle. Here, A, B, C are 3 points on the circle. So, that will satisfy the condition that it can be any point on the circle. So, A, B, C are 3 points on the circle here. The angle subtended at the center, which I named as angle 2, angle 6 and angle 10. So this 2 here I've intentionally named it as 1. So that is actually half of this angle. Here it's angle 6. Here I named angle 3. The ratio is again 2 by 1. I took angle 10 here and angle 5 here. Ratio wise it's still 2 by 1. So sum of these angles in the center is 360. Sum of these 3 angles is 180. So that 2 by 1 is still maintained. So in the previous explanation, I help you understand 2 by 1 extended to a straight angle to a right angle. Here, 2 by 1 extended to a circle by a triangle. And these are the easy ways to apply 2 by 1 to things which you already know. So this is how you can make learning very interesting, and thereby it's becoming easy anyway. So while solving questions using 2 by 1, you will find it very easy to use going forward. Angles in the same segment of a circle are equal. That is, if I take a circle like this, if I consider an arc PQ, angle PAQ equal to angle PCQ, because PCQ and PAQ are angles in the same segment. So we need to prove that these two angles are equal. So for that, first we can write down angle POQ equal to 2 times angle PAQ. That is from the previous theorem of 2 by 1, because angle subtended at the center is 2 times angle subtended at any point on the circle. Here is A is any point on the remaining part of the circle. Same way, if we take another point C on the remaining part of the circle, we can also write down angle POQ equal to 2 times angle PCQ. The reason is because of the same theorem. Now, if you compare this 1 and 2, what we will get is we can directly write down that angle PAQ equal to angle PCQ. Hence, the theorem is proved. That is, angles in the same segment are equal. So it's very easy to understand. We just need to consider 2 separate points A and C, and we know that angle PAQ, 2 times angle PAQ is angle POQ, 2 times angle PCQ is also angle POQ. So if you compare these two, we can directly write down that these two angles are equal. That's a very simple proof. Now, this is the converse of the previous theorem. So theorem can be stated like this. If a line segment joining 2 points A and B subtends equal angles at 2 other points lying on the same side of the line segment, then the 4 points lie on a circle, or that is, they are concyclic. So let me help you understand this. If there is a line AB subtending equal angles at C and D, that is angle ACB equal to angle ADB, in that case, A, B, C, D are concyclic. So this is what we need to prove. That A, B, C, D lie on a circle is what we need to prove. So for that, first you draw a circle through A, C and B, because through 3 points we can draw only one and only one circle. Suppose it is not passing through D, then it will intersect AD at E or E dash. Now if points A, C, E, B lie on a circle, then angle ACB will be equal to angle AEB, because they are angles in the same segment. Now we also know that angle ACB is equal to angle ADB, because that's given. So if you compare these two, angle AEB equal to angle ADB, now this is practically possible only when E is coinciding with D. Hence, we prove that A, B, C, D are concyclic or that they lie on a circle. So it's a very simple proof. Now what is the method? If a line segment, what is the theorem? Line segment, if it is subtending equal angles at two other points on the same side of the line segment, then all the 4 points are concyclic. So that theorem just got proved. Now let's understand what are cyclic quadrilaterals. A quadrilateral is called a cyclic quadrilateral if all the 4 vertices of it lie on a circle. That is, to visualize, if I take a circle like this, how do we get a cyclic quadrilateral? Take 4 points A, B, C, D. And if I join them, since all 4 of them are on the circle, we can say that quadrilateral ABCD is a cyclic quadrilateral. Let's look at some important properties based on cyclic quadrilaterals next. So the first theorem, the most important one here is sum of either pair of opposite angles of a cyclic quadrilateral is 180 degree. That is, in this cyclic quadrilateral, angle A plus angle C is equal to 180 degree. Same way, angle B plus angle D equal to 180 degree. So it's a very simple theorem. If you take sum of opposite angles in a cyclic quadrilateral, they are supplementary. That is, they'll add up to 180 degree. We will see the proof why this is 180 degree. We will prove this theorem next. To prove this theorem in a cyclic quadrilateral, opposite angles will add up to 180. It's a very simple proof. So take the circle, take 4 points A, B, C, D. If I join, I'll get a cyclic quadrilateral A, B, C, D. We need to prove that angle A plus angle C is equal to 180 and angle B plus angle D equal to 180. To prove this, first join AC and BD. If I name the angles the way it is given, if I consider segment AB, angle 1 equal to angle 4 because they are angles in the same segment AB. If I consider segment BC, angle 2 equal to angle 3 because they are also angles in the same segment BC. Now, if I take sum of these two, angle 1 plus angle 2 equal to angle 4 plus angle 3, which is equal to angle D, right? Angle 3 plus angle 4 is nothing but angle D. After that, consider triangle ABC, this particular triangle. In this triangle, angle 1 plus angle 2 plus angle B, that's equal to 180 because they are angles in a triangle. So sum of angles in a triangle is 180 degree. Angle 1 plus angle 2, I can replace it by angle D from the previous statement. So I can rewrite angle D plus angle B equal to 180 degree. That is, these two angles, angle D plus angle B equal to 180 degree. Similarly, now angle A plus angle C will also be equal to 180. Reason being, A plus B plus C plus D is 360. We also got B plus D as 180. So the remaining two, that is angle A plus angle C equal to 180 degree. So this way, we can easily prove that sum of opposite angles equal to 180 degree in a cyclic quadrilateral. So what we did here is nothing but, first, just to recap, consider segment AB so that angle 1 equal to angle 4. So the angles which are getting highlighted now. Then consider angle segment BC so that angle 2 and angle 3 are equal. They are getting highlighted. Now we know that if we take sum of these two, angle 1 plus angle 2 equal to angle 4 plus angle 3, which is equal to angle D. Then just consider this particular triangle so that 1 plus 2 plus angle 1 plus angle 2 plus angle B is equal to 180 degree. 1 and 2 you can replace it by angle D. So we got angle D plus angle B as 180 degree. That is sum of opposite angles equal to 180 degree. So it's a very simple proof, which I am sure all of you will be able to write down. And you don't need to memorize this at all. Now, converse of this theorem will be if sum of the pairs of opposite angles of a quadrilateral, if it's 180 degree, then the quadrilateral will be a cyclic quadrilateral. This also can be easily proved. So this is also an important theorem. It's just exactly the converse of, because in a cyclic quadrilateral, opposite angles will add up to 180 degree. The converse is, if sum of the pairs of opposite angles in a quadrilateral, if it's 180 degree, then the quadrilateral is cyclic. That is, if I take a quadrilateral ABCD, where A plus C equal to angle A plus angle C is equal to 180 degree, then this quadrilateral will be cyclic. So it's a very simple theorem which can be used again while solving questions. This is a good question. We need to prove that quadrilateral formed, if possible, by the internal angle bisectors of any quadrilateral is a cyclic quadrilateral. So let's take a quadrilateral ABCD. Now the internal angle bisectors, they form a quadrilateral EFGH. We need to prove that EFGH is cyclic. So for that, let's name the angles the way it is here. Angle 1 will be equal to angle AEB because they are vertically opposite, equal to 180 minus angle 2 minus angle 3. Reason being, in triangle AEB, sum of angles is 180. Now, what is angle 2? That is half of angle A. And what is angle 3? That is half of angle B because these are angle bisectors. So we can write that angle 1 is equal to 180 minus half of angle A plus angle B. Now, same way, angle 4 in this quadrilateral EFGH equal to angle CGD, which is equal to 180 minus angle 5 minus angle 6. Reason being, CGD is a triangle. So sum of angles equal to 180. Now what is angle 5? That's half of angle C. And what is angle 6? That's half of angle D. So this can be written as 180 minus of half of angle C plus angle D. Now, if I take sum of angle 1, and angle 4, I'll get 360 minus of half of angle A plus angle B plus angle C plus angle D, which is nothing but 360 minus half of 360 because A, B, C, D all added up will be 360 because they are angles in a quadrilateral. So we'll get angle 1 plus angle 4 equal to 180 degree. Since opposite angles are adding up to 180 degree in a quadrilateral, we know that the quadrilateral is a cyclic quadrilateral. So it's easily proved that EFGH is a cyclic quadrilateral. That is, angle bisectors in a quadrilateral will form a cyclic quadrilateral. Very easy. Now it's a very simple question based on cyclic quadrilaterals. So in this diagram, angle CAD equal to angle DBC because they are angles in the same segment and that's equal to 55 degrees. Angles in the same segment CD. Now angle A, this complete angle will be equal to angle CAD plus angle BAC, which is 55 plus 45 equal to 100. Now angle A plus angle C equal to 180 degrees because they are opposite angles in a cyclic quadrilateral. So getting angle C, which is nothing but angle BCD only, is nothing but 180. From 180 degree, if you subtract this 100, you will get the answer as 80 degrees. So it's a very simple question. You can immediately mark the answer. Now this is also a very simple question. To do this, first join AB. Now angle ABD will be 90 degree because that's angle in a semicircle. Angle ABC is also 90 degree because of the same reason. So if I take angle ABD plus angle ABC, it will become 90 plus 90 equal to 180 degree. Therefore, DBC is a line, that is B lies on the line segment DC.